Good morning, everybody. I hope today's presentation will be as successful as yesterday. As an invited speaker, Professor Shahin from Ege University will give a talk titled Conformal Riemann Maps from Kaehler Manifolds to Riemann Manifold. Please share your screen, Professor Shahin.
Okay, thank you very much.
You're welcome.
First of all, I'd like to thank the organizer and Professor Furkan Yıldırım on behalf of the organizing committee. It is my pleasure to be here and good morning from Izmir to everybody in this symposium. Now, like you said, my title will be Conformal Riemannian Maps from Kaehler Manifolds to Riemannian Manifolds. Let me begin by some motivation why we need to study conformal Riemannian map. Of course, I need to start by very special case or very basic things. If you compare the differential geometry or manifold theory to the other branches of the mathematics, it's seen that the appropriate maps are very limited. So if you think about the basic maps, the first thing comes to my mind or everybody's minds is that the surface. Actually, surface is a isometric immersion between two Riemannian manifolds. But when we consider, when we thought the surface in three-dimensional space, we don't use the term of the isometric immersions, but we just say that the surface. But actually, it is a map from two-dimensional space to the three-dimensional space. So in this respect, we have very basic map in terms of the general maps. But in the generalization, we see the isometric immersions or the submanifold theory becomes very attractive and very active study in the late 60s up to now. But there are also some another map. It's called Riemannian submersions. Although it's not very famous or very popular like the isometric immersions, but it's very important because if you want to find some spatial manifolds with some spatial certain curvatures, you need to use, or it's a usable tool to use the Riemannian submersions. If you compare two notions, isometric immersions and Riemannian submersions, isometric immersions are like an embedding, and if you think about, you are going from the low dimensional space to the bigger dimensional space. But submersions, or spatially Riemannian submersions, it is the projections, if you think about the very tough manner. So basically we have two notions here. One is isometric immersions, the other one Riemannian submersions. But again, if you consider the very general cases, these two maps are very special. So we need very general terms to compare the two manifolds. Of course, these general map should include some spatial or nice properties, because when you consider the two manifolds to compare, especially for Riemannian manifolds, you need to use the metric to compare the manifolds, because metric determines everything about the manifolds, curvature, connections, and other things. So in this way, Fisher in 1992 defined the Riemannian map. Riemannian map is a map such that it gives the isometric map or isometry between some part of the manifold, the total manifold or the source manifold to base manifold or range of the this map. So again, we have some isometry, but it is not like the immersion case or submersion case. So in this case, we have spatial one. Okay. So, okay, here formal definition. We have two Riemannian manifold, M1 and M2, and there is a F between them, and we denote the perpendicular space to the kernel F star by kernel F star perpendicular, and the range of this F, actually the range of the derivative of this map by range of F star. So if there is a isometry between these two space, one is kernel F star perpendicular with this Riemannian matrix G1 and the range of F with the matrix G2, and if there is a isometry like this one, then we call this map is a Riemannian map. So if you consider the kernel F as a 0, then you have isometric immersion. If you have range of F star perpendicular as a 0, then you have a Riemannian submersion. So this map is a generalization both isometric immersion and Riemannian submersion. But if you consider the map or general terms to compare the two shapes, two geometric object, you need to use the conformal case. In this case, of course, you have an isometry, but you have also conformal thing. It means it preserves the angle and like the other things. So it is more general case in this case. So in 2010, I defined this. Okay, I defined the conformal Riemannian map by considering a lambda function here, lambda square. So in this case, you have a conformal isometry, maybe we can say. In this case, you have the target manifold N, the base manifold or total manifold M, and you have a F between these two Riemannian manifolds. Also, you have these Gn and Gm related by this function. So if the function lambda is 1, then you have Riemannian map. Otherwise, you have some general conformal map. So you see, in this case, if you consider lambda constant and some certain restriction on the range and kernel F star, then again you have conformal or you have isometric immersion and Riemannian submersion. And this one is also generalization of the conformal immersions, which is very active research area. Also, it is a generalization conformal submersions. These conformal submersions is very important because it is vital geometric object when you study the harmonic map. So in this way, we generalize this Riemannian map, and this also gives certain positive answer our question, because we say that there is a restriction or there is a few maps between Riemannian manifolds or in geometry, in differential geometry. So we need more general case to compare the manifolds. So this is one presentation, one notion to give a positive answer to this question. in my talk, I will consider this one. Okay. So I will introduce conformal Riemannian map like I did here, and then I will consider the complex manifold as a source manifold, and then according to the behavior of these conformal Riemannian map, actually the vertical space of this Riemannian map, I will give some new notions related to these conformal Riemannian maps. So let me begin by some basic notions we need to mention about these new notions, new definitions. So the first one is second fundamental form, and in this case we have two Riemannian manifold and F between them, and the second fundamental form is defined by 2. You can think about this as a generalization, the second fundamental form of the surface or submanifold. Indeed, if you consider the isometric immersions, this one reduced to the second fundamental form of the isometric immersion. But here we have general case, because in this case you need to use pullback bundle to define this notion. And like the Weingarten formula here, we have 3 as a Weingarten formula. But here we need to use the pullback connection to define this notion. So by using the Riemannian submersions, we have some other connection formula, and it is denoted by 5 and 6. So we need to use the basic vector field. So basic vector field, actually it is a vector field, projectable vector field, but also it is a horizontal. So it is belong to the space of the kernel perpendicular. Okay, here we will use this theorem very often in this talk, and it gives the idea, the behavior of the second fundamental form for conformal Riemannian map. So basically it says, if you have conformal Riemannian map between two Riemannian manifolds, then your second fundamental form takes spatial form given by 7. You see, for the restriction on the range of F star, we have this one. So you can use this one to define the more general formula by using this and the general formula for pullback connection. So here, like we did in the submanifold case, we put the perpendicular notion symbol to denote the perpendicular part of this second fundamental form. So here our first definition. By using the almost complex map between two Kaehlerian manifold or two complex manifold generally, we can give the holomorphic conformally Riemannian map. In this case, as the natural one, first you have conformal Riemannian map, and then you put this condition. Your F should be almost complex map on the horizontal distribution. So here J prime denotes the complex structure of the N, which is almost Hermitian manifold, and J is the complex structure for the Kaehler manifold M. So the natural example of the holomorphic conformal Riemannian maps are holomorphic submersions and holomorphic Riemannian maps. Okay, also we have some special example here between R4 and R4. So you see we have one numerical example for this case. So you see this one we illustrated our notion by giving the one specific example of holomorphic conformal Riemannian map. So like this one, we can define the invariant conformal Riemannian map. Basically, if the vertical space, it means the kernel F star, is invariant under this J, the complex structure of this M, which is Kaehlerian manifold, then we call this one is invariant conformal Riemannian map. So we have this example for this case, but here I need to emphasize that any invariant conformal Riemannian map may not be holomorphic conformal Riemannian map. So there is a distinction between these two notions. Of course, if you have holomorphic conformal Riemannian map, in this case your Riemannian map should be also invariant conformal Riemannian map. But the converse is not correct generally. So here we have another notion. It's called conformal anti-invariant Riemannian map. So if this one is usual, contrary to the before notion, in this case, if your vertical space is anti-invariant under the complex structure Jm here, then we call this one conformal anti-invariant Riemannian map. So it means you are carrying your all vector fields belongs to the kernel F star to the horizontal space. So this one is actually a generalization of the conformal anti-invariant Riemannian submersions. So if in the spatial case, if the dimension of these kernel F star and the kernel F star perpendicular are same, then in this case we call the Lagrangian conformal Riemannian map. So this one gives very rich geometric notion for this theory. Of course, the natural examples of this notion is anti-invariant Riemannian submersions, conformal anti-invariant Riemannian submersions, anti-invariant Riemannian map. All of these notions, these classes are examples of these conformal anti-invariant Riemannian map. So here we have some spatial numerical examples also. You see in this case we are going from R4 to the R5, and here the spatial calculations about this one. So about the geometry, I told there is a nice or rich geometric properties. So this gives you new conditions to define a totally geodesic foliation on the total manifold. So we have kernel F star as a vertical space. We have some new conditions to be totally geodesic. It means the integral manifolds of this distribution is totally geodesic. So you see we have equivalent conditions for this notion. Also we have new notion, polyharmonic map. You can think about the polyharmonic map. It is a map very close to the harmonic map, but it is not necessarily always should be. Well, where this idea coming from is that we know any holomorphic map between two Kaehlerian manifolds, it is always a harmonic map. And if you look at the second fundamental form of the holomorphic map, you see this condition is satisfied automatically. So this is the idea to use this notion. It's called the polyharmonic map. In our cases, we have several distribution in our total manifold. So we can use this polyharmonic map for some spatial cases, and we can define the new polyharmonic map. So one is this one. We call this conformal anti-invariant Riemannian map kernel F star perpendicular polyharmonic map if it is satisfied this equation, but only for xy belongs to the kernel F star perpendicular. So not general case, but only for this case. So this notion gives new characterization for the distribution kernel F star to be totally geodesic. So here is the one theorem about this one. You see, in terms of the notion of the Riemannian submatrix and Riemannian map.
Bir şeyler oluyor.
Okay. So here we can also give the equivalent conditions for this map, and here you see the in terms of the gradient and the connection of the base manifold. So here we have another notion. It's called horizontally homothetic map. So basically this is a map. The only the kernel cases is not constant, but in the horizontal part of this function we call the dilation or the lambda in the beginning. And if this one is constant along the horizontal distribution, we call this one horizontal homothetic map. So this notion also, conformal anti-invariant Riemannian map, gives a characterization for the horizontal homothetic map in terms of the distribution J kernel F star. Okay, these and other conditions. So we, by copying this condition, we call the mixed polar harmonic map, and by using this notion, we give another condition. Here, another one, kernel F star polar harmonic map. So in this way, we have another characterization. Okay. So you see, we have several new characterization for the this kind of conformal Riemannian map by using the complex geometry and the maps theory itself. So by generalization of the conformal anti-invariant Riemannian map and conformal Riemannian map, we have conformal semi-invariant Riemannian map. In this case, on the kernel F star, on the vertical distribution, we have two distributions. One is called D1 and the other one is called D2. And these two distributions are orthogonal to each other. So if the D1 is invariant under this complex structure and anti-invariant under the complex D2 is anti-invariant under the complex structure, we call this one is conformal semi-invariant Riemannian map. So in this case, if D1 is 0, you have conformal anti-invariant Riemannian map. If D2 is 0, you have conformal Riemannian map. So this is a generalization, both conformal Riemannian map, conformal holomorphic invariant Riemannian map, and conformal anti-invariant Riemannian map. This above definition is a generalization of the semi-invariant Riemannian map introduced by me several years ago. So by using this idea, you have this decomposition, the vertical space. So in this case, your vertical space consists of with two distributions. One is D1, but the other one is D2. This is a generalization also, is a semi-invariant Riemannian submeshing. So you see, it is very general notion in terms of this theory.
Excuse me, Professor Şahin. You have 5 minutes left.
Okay, thank you very much. So by using this notion, semi-invariant Riemannian map, we have some nice characterization. So I passed the examples. So the first one is, it shows that D2 is always integrable. And we also have some other characterization about the leaves of the distribution by using this polar harmonic map and the A itself. Okay. So because I have 5 minutes left here, so let me give another notion. Okay. So another generalization of the holomorphic invariant Riemannian map, conformal invariant Riemannian map, and conformal anti-invariant Riemannian map is the conformal slant Riemannian map. In this case, you have kernel F star, and when you take the vector field on this space, and when you apply the complex map, complex structure, then the angle between these vector field and kernel F star is constant. Of course, this is not always case, because sometimes may not be the constant. But in this case, we have another generalization, because if this theta if this angle is 0, you obtain the invariant conformal Riemannian map. If this angle is 90 degrees, if pi or 2 radian, then you have a conformal anti-invariant Riemannian map. And also I need to emphasize here, there is no inclusion relation between conformal slant Riemannian map and conformal semi-invariant Riemannian map. So these are the separate notions. So in this case, this notion, this conformal slant Riemannian map, is also generalization of the slant Riemannian map given in 2013. So by using this one, we have some examples. Also, we have some characterization. You see, for the conformal slant Riemannian map, we have this characterization. This one, phi here is a morphism. So also we have, let me give, okay, horizontal homolytic map. You see, also pluriharmonic map for these cases, and okay, here example. So you see, by using the conformal slant Riemannian map, we have more general cases for the maps in Riemannian geometry. I think I will stop here. Thank you for your listening, and if you have any questions, I can answer them.
Thank you for your contribution to symposium, Professor Şahin.
Okay, Professor Özkan, maybe I should add this one. All these materials can be found my former PhD students, Şener Yanan PhD student, PhD thesis, because all these the results I presented here can be seen in his PhD thesis. Also, he obtained some more results about these topics, and you can see here. And let me show my references, and these are the references.
Thank you so much for information about your presentation. Are there any question or comment?
Can I speak?
Please.
Bayram Şahin is a very valuable professor who has more than 1,500 citations and 150 publications in geometry. Thank you very much for this good presentation.
Okay, let me use this opportunity to invite the young geometrists to study Riemannian maps, because as you see, nowadays many young Turk and other geometrists studying maybe submanifolds, surface, and your group bundle theory. But I can assure you there is a huge opportunity in this theory, and because we just established the main notions and main structure equations here, and there is a many new area to explore. So I invite the young geometrists to explore, to study in this area.
Thank you so much.
Thanks.
Is there any question? No question. Thank you again,
Thank you
Professor
again
Şahin.
for this nice organization. Have a nice day.